For this question, we have an output power is determined by using the arrangement shown below. We have this wheel is rotating because of the motor. There is a belt that goes around the motor. There is a weight on one side, a weight on the other. It looks like they've intentionally shown this one to be heavier, which has the effect of making lifting this one easier, or vice versa. So in this case, you see the motor is going like in this direction. So although gravity is pulling it down like this, gravity is pulling that one down, and the motor is working this way. So with this as a counterweight, it makes this easier to raise because of this additional weight on this side. So the belt has weights to its ends, has a circumference S. Let's put that there, S. Rotating R revolutions per second. R revolutions per second. Correct expression for the output power of the motor. Well, we'll start with our with power. Power equals work divided by time is force times distance over time is FV. So those are the possibilities we have there. And what do we know? There are forces going on, so we're now looking more like this in this direction. So we need to know what the forces are that are applied. So drawing a free body diagram for W2, we have FG2 and we have tension 2. And for 1, we have FG1 and we have tension 1. Now the pulley is changing the direction, so to make this simpler for us to see, we're going to rotate these. So here we have FG2, T2, and over here we have FG1, which is, we can see, is opposite to FG2, and this is T1, positive direction, negative direction. We know the net force is always the sum of the forces, and the net force produces an acceleration, but what we're looking for is the net force here. So we'll leave it at that, and the sum of the forces are minus Fg2 plus T2 minus T1 plus Fg1. And because this is one continuous belt, we've studied this in tension that inside that material, the forces are equal and opposite everywhere. So T2 and T1 are equal to each other, and so they drop out. Rearranging this conveniently, we have Fg1 minus Fg2, and that is our net force. So the weight of, and using their terminology, we have the weight of one minus the weight of the other. And so if that's the force, we need to know the distance. S is the circumference. So we have this circumference, and what's not obvious is that that distance S, it will rise the distance S every second, and so then the S per second, and we have a number of, so S is the distance times the revolutions per second. We have a distance which is divided by the time, which is an RS or SR. So we can see all of these have a times SR with them. So that's not something we need to worry about. The question then is, what is the force involved? The question that remains then for us is the force involved just about moving W1? In other words, does W2 not matter? And for B, W2, does W1 not matter? Well, it seems like those are two answers that are presenting the same problem, but for two of the different masses in it. So suggest they both are incorrect. It is different. The work that this has to do, the power output of this motor is going to be different depending on the masses on each side and the difference between those masses. If we added many more weights to this side, we know that motor is going to have to work harder if it travels at the same speed, same R. So it can't be due to just one or the other. And so the question then becomes, is it about the addition of those weights, or is it about the difference between those two weights? We can see already that the force has to do with the difference of the two weights. The difference of the two weights. And choice C is about the difference in the two weights. And how we know it's the difference of the two weights, if we were to go a little further with this, if we were to compare two different cases, let's suppose we have this case and this case like the one they gave us. But now let's suppose we can see that in this case, it's going to have to do more work. Not so much because the mass is more, but it's because the difference is larger. And when the difference is larger, the motor has to make up for that difference. And yet another way to look at it is, let's suppose now this is a free pulley. Or you were pulling on that free pulley. You were doing the work. And you have case A and you have case B. If these two are the same, you have to do no work. All the work you're doing is just going into the changing the speed, the kinetic energy. But in this second case over here, you can see you have to do a heck of a lot more work. It's much harder because the difference in the masses is so much greater.